Namaskar and hello. Welcome to Shridevi Classes YouTube channel, a channel designed to inculcate interest and confidence in science and engineering education and to build strong core competency with right understanding and clarity of concept. Today in our playlist, class 12th physics, we'll study electric field of charged conductor sphere and understand solutions of problems related to ratio calculations among strength of electric field, electric potential, charge density, amount of charge over the surface of conductor sphere having different radiuses. Let's start. In these ratio calculation problems, we have given two charged conductor spheres of radius r1 and radius r2 having surface charge q1 and q2, surface electric field intensity E1 and E2, and surface potential and surface charge density respectively V1 sigma 1 on r1 radius sphere and V2 and sigma 2 on the sphere of radius r2. For ratio calculation or comparison, we have to use various relations. An isolated charged conductor sphere acts like a point charge acting from its center. So over the surface having radius r, the spherical charge q produce electric field on the surface equal to kq upon r square, and this relation clearly indicate that strength of electric field is directly proportional to amount of charge on the spherical surface and is inverse of the square of the radius of sphere. Similarly, charge density, charge per unit area of spherical surface, the spherical surface of radius r got a area 4 pi r square, so charge density got a relation q upon 4 pi r square, and this charge density sigma is again directly proportional to amount of charge and is inverse of the square of radius of sphere. Now in the field of isolated charged sphere, amount of work done in bringing a unit positive charge over the surface of sphere known as potential of charged sphere is given as kq by r, where r is radius of sphere and q is amount of charge on that spherical conductor. Again, potential is directly proportional to amount of charge as electric field intensity or surface charge density, but it is just inverse of radius of sphere and not inverse of square of radius as it is electric field intensity or surface charge density. If we have two spheres of identical radius, that means r1 and r2 is equal, then in that case electric field, potential and surface charge density all become proportional to amount of charge on the surface. So we can say ratio of electric field intensities on two spheres or ratio of surface charge density or ratio of potential is directly ratio of charges on sphere. So a sphere having higher amount of charge would have higher amount of electric field intensity, surface charge density or potential for the same radius. So if two sphere of same radius got charge q1 and q2 in the ratio of 1:2, then sphere having double charge would have double surface charge density for the same spherical surface area. So it would have double electric field and double value of surface potential. So the ratio of electric field is as per ratio of charges. For q1:q2 ratio 1:2, electric field E1:E2 would have ratio 1:2. If two isolated spheres got different radius r1 and r2 but have the same amount of charge over their surfaces, then in that case the relation of electric field intensity on the surface of charged sphere given as kq upon r square become just inverse of the square of the distance. So sphere of higher radius would have smaller amount of surface electric field intensity for same amount of surface charge, and if r1 and r2 got a ratio of 1:2, then electric field on the surface of these two spheres with identical amount of charge or the surface charge density for identical amount of charge but radius in the ratio of 1:2 would have a ratio of 2:1 square or 4:1. That means surface of smaller radius sphere with the same amount of charge would have 4 times surface charge density and surface electric field intensity. Both electric field intensity and surface charge density are inverse of the square of the radius of sphere. So when E1 or sigma 1 is at numerator side, r1 square to the other side is in denominator position. Similarly for E2 and sigma 2 in denominator side, r2 square is at numerator of second side. Now the surface potential potential for a spherical charge q at a spherical radius r is given by this relation, and for identical amount of charge on two spheres of radius r1 and r2, the surface potential is inverse of the radius. It is also clear that spherical charge will act as a point charge acting from center position. So at r1 distance, a point charge will produce electric field kq upon r. So for the same amount of charge on two spheres, the sphere of higher radius would have smaller potential, and potential is inverse of radius. If two radius got ratio 1:2, then bigger sphere of double radius would have half of surface potential value as compared to potential of smaller radius. When two isolated sphere of radius r1 and r2 have identical value of surface electric field intensity or surface charge density, E1 is equal to E2 or sigma 1 is equal to sigma 2, then the relation of electric field intensity or surface charge density clearly indicate that charge on those spherical surface become proportional to radius square. So q1 upon q2 ratio is equal to square of the ratio of radiuses of two spheres. Say r1 and r2 got a ratio 1:2, r2 is 2 times of r1, then in that case total spherical surface area of this double radius sphere would be 4 times, and for same surface charge density, the total amount of charge on this spherical surface of double radius become 4 times. If one has to find out ratio of potentials on surface of these two spheres of different radius for identical value of electric field intensity, this surface potential relation can be modified by multiplication of r in numerator and denominator, and it become kq upon r square multiplied by r. Now kq upon r square is surface electric field intensity, which is constant for both sphere of different radius, and this relation says that potential of sphere become proportional to radius of sphere. This can also be tested from this relation. For identical electric field intensity, charge on spherical surface is directly proportional to radius square. So if q is proportional to r square and there is 1 r in denominator, potential become proportional to radius of sphere, and the ratio of potential on two spheres with identical surface charge density or surface electric field intensity is equal to r1 upon r2. The most popular examination pattern about ratio calculation of two isolated charge conductive sphere is when two sphere got different radius r1 and r2 but have the same surface potential value. Then in that case, potential relation V is equal to kq by r clearly indicate that charge on spherical surface become directly proportional to radius of sphere, or charge or radius ratio is the same for both spheres for identical potential values. So if r1 and r2 radius are in the ratio of 1:2, then the charge on bigger radius becomes 2 times of charge of smaller radius sphere for identical value of potential of the two sphere. Now this relation of electric field intensity can be modified as kq by r multiplied by 1 by r, and since potential of two sphere is same, kq by r is a constant, then electric field intensity become an inverse ratio of radius. This is also verified from this proportionality relation, as charge on spherical surface with identical potential is directly proportional to radius of sphere. So this q is proportional to radius of sphere, and this denominator got square of radius, so the ratio become 1 by r. So electric field is inverse of radius of sphere. So ratio of electric field intensity and surface charge density of two spheres which is identical but is inverse of the radius of sphere as illustrated in this blue frame, and we can verify that if r2 is 2 times of r1, then for identical potential value this bigger sphere got double amount of charge but 4 times spherical surface area. So charge density become 1/2 of smaller sphere for identical value of potential on the two spheres, and as charge density and electric field intensity are proportional to each other, so electric field intensity of this bigger sphere is also half, as it is clear that electric field intensity is inverse of radius for identical value of potentials. Let's analyze a very popular textbook problem. We have given two spheres of radius r1 and r2 with equal amount of charges on that, and that charge is capital Q. If the radius are different, then surface charge on radius of sphere produce potential given by this relation, and for identical amount of charge on two spheres, sphere of smaller radius will have higher potential. If these two charged conductor spheres having different potentials are connected together by a conductor wire, then due to potential difference, charge will start moving from high potential sphere to low potential sphere till the potential of two spheres become identical, and at that identical potential conditions, when the two spheres are again separated and kept isolated and the common potential comes to be capital V, then we have to find out amount of previous charge on two spheres in terms of this common potential. So we know that finally both spheres would have same potential, and this common potential on R1 radius sphere with Q1 charge is given by K Q1 upon R1, and similarly in second sphere the common potential condition will have charge Q2 over radius R2, and the potential relation KQ2 upon R2 and potential relation of KQ1 upon R1 is equal for common identical potential, and this relation modified as charge of R1 radius in terms of common potential and charge of R2 radius pair in terms of common potential can be obtained. And if we apply law of conservation of charge, then in this charge transfer process, charge before transfer, both sphere of radius R1 and R2 initially got identical charge capital Q, and sum of that two charges 2 capital Q, and finally the two sphere of radius R1 got Q1 charge and radius R2 got Q2 charge. Then sum of charge after equalization of potential and before connections remains the same, and if we replace Q1 and Q2 in terms of common potential, then we can find out amount of previous charge Q as common potential divided by 2K multiplied by R1 plus R2. Problem of concentric charged spherical cells are also very common in our examinations. We are given a solid or hollow spherical charge of radius small r and surface charge small q, and with the same center there is another spherical shell of capital R radius with charge capital Q. We have to find out electric field and potential at this r dash distance position from common center. We'll apply superposition principle, and resultant electric field is electric field contribution by inner spherical charge of small q and radius small r, and electric field contribution of outer spherical shell of capital Q charge. For this external position, this spherical charge of small q acts as a point charge from the center, and small q charge with distance of observation position from center r dash will produce electric field contribution kq r dash square. And for this outer spherical shell, electric field contribution at internal position is 0, so there won't be any electric field from capital Q charge. So resultant electric field at r dash distance by these two spherical charge distribution is kq upon r dash square. Similarly, to find out potential at r dash distance position as per superposition, the total potential is potential of inner spherical charge and outer spherical shell charge capital Q. This inner spherical charge acts like a point charge from center, and Q charge at r dash distance will produce potential kq upon r dash. And for outer spherical shell, the potential at inner position is same as that on the surface of spherical shell. So this Q charge on its spherical shell radius r produce potential kq upon capital R. So this potential contribution of outer spherical shell and this contribution of inner spherical charge will be added as per superposition principle to get total potential. If we want to find out electric field on the surface of this inner spherical body at a distance r from center, for electric field and potential calculation on this inner sphere, we can change this r dash by radius of inner spherical shell small r, and electric field contribution over this surface of inner sphere will become kq upon r square, as at internal position outer charge won't produce any electric field contribution, and similarly potential at this inner sphere become potential due to small q charge at its spherical radius r, and potential contribution of this outer spherical shell charge is kq upon capital R, the same potential as on its own surface. And if one want to find out electric field and potential at this center position, then there won't be any internal electric field. Similarly, if one want to know electric field and potential within this blue inner shell, then there won't be any internal electric field field in this conductor shell or solid spherical conductor, as all charge will reside only on its outer surface, and as there is no electric field inside this inner sphere, there won't be any potential difference. So potential on surface of this sphere given by this relation is also potential anywhere in this internal position. So potential at this central position is same as that of potential on the surface of inner sphere given by this relation, K small q upon r and K capital Q upon r respectively potential on individual charged surfaces. Let's finish this learning video with one important examination question. We have given two hollow concentric shell of radius small r and capital R with common center, and total charge capital Q is distributed among these two spherical shell with identical surface charge density. We have to find out potential at the common center of these two shells. So if identical surface charge density is sigma, then over this small spherical shell of small r radius having area 4 pi r square, total charge Q1 is 4 pi sigma r square. Similarly, on this bigger spherical shell of capital R radius, the total surface area of that shell is 4 pi capital R square, and with surface charge density sigma, the total charge on bigger shell is 4 pi sigma r square, and the total charge is given. Capital Q is the sum of these two. Now we can write surface charge density on smaller spherical shell of spherical surface area 4 pi r square with charge Q1. Similarly, bigger shell got radius capital R, surface area 4 pi r square, and charge per unit area is the identical charge density. And if we add the two charge, then total charge divided by total surface area of smaller shell and bigger shell become the common charge density. Now using these relation, we can write charge on first pair in terms of total charge and the radius of small and big spherical shell, as this as 4 pi from both sides get cancel out and r square to other side when shifted get multiplied by q in numerator as shown here. Similarly for q2, this capital Q charge get multiplied with r square, and we got relation of charge on bigger spherical shell in terms of total charge. Now the resultant potential at common center can be obtained by superposition principle. If only small q1 charge act on this spherical shell of radius small r, then potential at internal position is same as potential on its surface, and that is k q1 upon r. Similarly, if only q2 charge act alone, then potential contribution of q2 charge on this internal position is same as that on its surface, and surface potential of q2 charge is k q2 upon r. If we replace q1 and q2 in terms of total amount of charge capital Q and simplify things, now we can replace q1 in terms of capital Q, and this replacement will produce capital Q and r square plus capital R square as common, and this r square divided by this small r produce small r in numerator. Similarly, q2 when replaced by this relation, this r square is divided by this capital R, remaining capital Q and r square plus capital R square brought common, we will get capital R in summation. So this become finally the common center potential of these two concentric shell having total charge capital Q and radius small r and capital R. We hope the solution of these selected problems will enhance your confidence and improve your score in examination. Our other learning video of same playlist will improve your physics understanding and remove all your confusions and create clarity of concept. This topic is finished here, and we'll meet again with similar informative wonderful learning video. Thank you once again.